Welcome to AI Paper Podcasts. We're the place where we dive into the latest research shaping, well, the future of AI.
That's right.
And today, we're looking at a really fascinating paper from ByteDance Seed. It's called Seeing, Listening, Remembering, and Reasoning, a Multimodal Agent with Long-Term Memory. Quite a title.
It really signals the ambition, doesn't it? Seeing, listening, remembering, and reasoning covers a lot of ground.
Absolutely. Imagine a future where your smart home agent, it doesn't just wait for your command, but it kind of knows you. Like it knows your coffee preferences, maybe not because you programmed it in, but because it's just been observing you day in, day out, seeing, listening, remembering things over weeks, months, kind of like a person would.
Exactly. And that's not science fiction anymore, or at least the path there is getting clearer.
Yeah.
That's the future this paper and the framework they built, M3 Agent, are really pushing toward.
Okay, so let's get straight to it. For anyone short on time, here's the quick rundown, the key insights in about a minute.
Go for it.
All right, so this deep dive is all about M3 Agent. It's a new multimodal agent framework from ByteDance Seed, and its big thing is long-term memory.
Right.
It actually tries to mimic human memory. It processes real-time video and audio, building up two kinds of memory. Episodic, which is like concrete events, think Alice grabbed her coffee, and semantic, which is more general knowledge, like Alice likes coffee in the morning.
And importantly, this memory isn't just a jumble of facts. It's entity-centric, focused around specific people or objects, and it's multimodal, handling faces, voices, actions all together. This gives it a much deeper, more consistent understanding.
Yeah, and it's not just about storing stuff. M3 Agent performs autonomous reasoning. It thinks iteratively over multiple turns, pulling what it needs from memory to get tasks done.
Which is a big step beyond simple retrieval. And to test this, the researchers built M3 Bench, a new benchmark using long videos, some from a robot's point of view, others from the web, specifically designed to test this kind of memory-based reasoning.
And the punchline. M3 Agent, trained with reinforcement learning, significantly beats strong competitors, even things like agents using Gemini 1.5 Pro and GPT-4o. It's a really substantial leap towards AI with genuinely human-like long-term memory.
That's the gist. A big leap.
So our mission today is to unpack all of that, how M3 Agent processes info, how it builds memory, how it reasons, how they tested it, and why this is such a big deal for the future of AI.
Sounds good. Let's get into it.
All right, so we have this vision of the future robot. But how does M3 Agent actually, get us there? What's the core idea behind its design?
Well, think about what a truly useful household robot needs. The paper highlights three key things. First, it has to constantly perceive the world, right? Through cameras, microphones, multimodal sensors.
Okay, continuous perception. Makes sense.
Second, it can't just see things. It has to store those experiences in long-term memory. And crucially, it needs to build actual world knowledge from them over time. Not just fleeting observations, but understanding how things generally work.
Right, like learning rules or preferences.
Exactly. And third, it needs to reason over all that accumulated memory to guide its actions intelligently. You tell it to do something, it uses its past experiences and knowledge to figure out how.
Like a person learning and applying lessons. So M3 Agent is positioned as the solution to these challenges.
Precisely. It's a multimodal agent framework built around this idea of long-term memory. And the clever part is how it handles these things with two parallel processes running constantly.
Parallel processes. Okay, what are they?
You've got memorization. This process is always running, taking in the real-time video and audio streams, processing them clip by clip, and continuously building and updating that long-term memory, like it's constantly journaling its experiences.
Okay. Always learning, always updating. And the second process?
That's the control process. This kicks in when the agent gets an instruction. It interprets the command, then it reasons over the stored memory, pulling out relevant bits, and figures out how to execute the task.
So one part is constantly observing and remembering, the other is using that memory to act on goals.
Exactly. It's very much analogous to how our brains work, right? We're always taking in new info, building memories, while simultaneously using our existing knowledge to navigate the world and make decisions. This dual process is really key to its human-like approach.
Okay, that makes sense. So if it's remembering like a human, what does that memory actually look like inside the AI? How does it store these experiences? Let's dig into that memorization process.
Yeah, that's the core of it. M3 Agent draws inspiration from human cognition, creating two distinct types of memory from the video streams it sees. First, there's episodic memory.
Episodic, like specific episodes or events?
Exactly. It records concrete events. Things like Alice picks up the coffee cup and says, "I really need this caffeine boost." Or maybe Alice throws an empty plastic bottle into the green recycling bin. Specific moments in time.
Got it. Like snapshots of events. What's the other type?
The second type is semantic memory. And this is where it gets really clever, I think. It's where the agent derives more general knowledge from those specific episodes.
Ah, so it generalizes.
Right. So from seeing Alice grab coffee multiple mornings, it might infer the semantic knowledge. Alice typically drinks coffee in the morning. Or from the bottle throwing episode, the green bin is designated for recycling materials. It's building an understanding of patterns and rules.
That's a huge step beyond just recalling isolated events. How is this all stored? Is it just a big list?
No, it's much more structured. It's stored in a long-term memory database that can handle multimodal information, faces, voices, text descriptions, all linked together. And the really revolutionary part is its entity-centric organization.
Entity-centric, meaning focused on people, objects.
Exactly. Think about a person. Let's stick with Alice. Instead of having scattered facts like her face is stored here, her voice sample over there, her coffee preference somewhere else, M3 Agent links all information related to Alice together.
So Alice's face, her voice, the fact she likes coffee, it's all connected in a sort of graph.
Precisely. It builds these connections incrementally as it processes information and extracts that semantic knowledge. This is absolutely key for consistency. It helps the agent understand that the person it sees today is the same Alice it heard yesterday, even if she looks slightly different or sounds tired. It builds a coherent understanding of entities over time.
That sounds incredibly powerful for long-term interaction, but it also sounds really complex. How does it manage consistency when it's constantly bombarded with new information, this infinite stream problem?
Yeah, that's a massive challenge. You could easily end up with contradictory information or just get overwhelmed. M3 Agent tackles this in a couple of ways. First, it tries to preserve the original multimodal features, not just text summaries.
So it keeps the raw data, like the face image.
It keeps representations, yes. And it uses tools like facial recognition and speaker identification to create persistent IDs, like a stable face or voice aid. These different IDs are then linked to a shared character. So FaceID 123 and VoiceID 456 might both link to character 789, which represents Alice.
Okay, so that helps tie everything back to the same entity. But what if the tools make a mistake? Like, it briefly thinks VoiceID 456 belongs to Bob instead of Alice. Does the memory get corrupted?
Good question. It actually has a mechanism for that. It uses a weight-based voting system. As the agent sees more evidence correctly linking, say, VoiceID 456 to Alice, character 789, the weight or confidence of that link increases.
Ah, so the correct associations eventually win out over temporary errors.
Exactly. Over time, the stronger, correct links dominate and suppress the incorrect, weaker ones. It allows the system to self-correct and maintain robust knowledge, even if there are occasional glitches in perception.
Clever. And how does it actually retrieve information from this complex memory graph?
It has two main search tools. Think of them like specialized search functions. There's Search Node, which is good for finding specific entities or semantic facts, like retrieving everything known about character 789, or asking, what is the green bin used for?
Okay, for structured knowledge.
And then there's Search Clip. This lets the agent find relevant video clips from its episodic memory. Like, show me the moments when Alice was near the recycling bin. It allows grounding back to the original experiences.
Right, so it can pull up both general knowledge and specific past events.
Okay, so the agent is busy building this rich, structured, self-correcting memory. Now, how does it use it when I actually ask it to do something? Let's talk about the control and reasoning part.
Exactly. All that memory is useless if you can't act on it. When an instruction comes in like, find Alice's favorite mug,
Right.
the control process kicks in. It uses the long-term memory to reason about the task and figure out the steps.
And you mentioned earlier it's not just simple retrieval augmented generation, or RAG.
Right. Standard RAG often involves retrieving relevant info once, feeding it to a language model, and getting an answer. M3 Agent does something more sophisticated. It uses reinforcement learning, RL, to enable multi-turn reasoning and iterative memory retrieval.
Multi-turn, iterative. So it has a conversation with its own memory. Kind of, yeah. Instead of one lookup, it might perform a sequence of searches. It asks a question of his memory, gets some info, maybe realizes it needs something else, then formulates a new query based on the first result, and so on. It's this iterative process, guided by RL, that leads to higher success rates on complex tasks.
That sounds much more like how a person might think through a problem. How does it decide what to search for next in this iterative process?
It uses a multimodal large language model, MLLM, as the core decision maker, what they call the policy model. Based on the instruction and the current state of its reasoning, the MLLM decides which search tool to use, search clip or search node, and what query to issue.
So the MLLM is steering the search process turn by turn.
Exactly. And they use specific prompt structures to manage this interaction. A system prompt to set things up, an instruction prompt for each reasoning step, and a final prompt to signal when it thinks it's done.
Interesting. And training this whole thing must be complex. You mentioned the memorization and control parts were trained separately.
That's right. Conceptually, it's one system, but for practical training, they use different foundation models optimized for each task. For memorization, which needs strong multimodal understanding processing, video and audio, effectively they started with Qwen 2.5 Omni.
Okay, a powerful multimodal base.
And for control, which needs really strong reasoning and decision-making, they use Qwen 3, a powerful language model. Then, crucially, they fine-tuned that control model using reinforcement learning, specifically an algorithm called DPO.
DPO.
Yeah, it's a method particularly good for training agents to make sequences of decisions, like choosing which memory search to perform next. That RL step is vital for getting that effective, iterative reasoning behavior.
Okay, so a sophisticated agent needs a sophisticated test. This brings us to M3 Bench, the benchmark they developed. Why did they need to create a new one? Weren't existing video QA benchmarks good enough?
That's a key point. Most existing long video question answering, or LVQA, benchmarks were primarily focused on, let's say, lower level visual tasks. Things like recognizing actions, what is the person doing, or basic spatial temporal understanding. Was the red car there before the blue car?
So more about perception than reasoning.
Exactly.
Yeah.
They didn't really probe the higher level cognitive abilities that M3 Agent is designed for, things that heavily rely on integrating information over long periods, understanding relationships, inferring knowledge, using that long-term memory.
So M3 Bench was specifically built to test reasoning with long-term memory. Makes sense. Where did they get the videos?
They used two main sources to get diverse data. First, there's M3 Bench Robot. This has 100 real-world videos, actually captured from a robot's first-person perspective.
Wow, really? From a robot's eyes?
Yeah, designed to simulate what a robot might actually see moving around a house, like in kitchens or living rooms. They actually use human actors wearing head-mounted cameras as a practical way to get this kind of data. Gives you that unique, sometimes shaky, robot's eye view.
That's a clever way to simulate it. And the second source?
That's M3 Bench Web. This includes nearly 1,000 videos, 929, I think, sourced from YouTube. Things like vlogs, tutorials, reality shows. It brings in a much wider variety of content and scenarios.
Okay, the verse videos, what about the questions? Are they just simple recall?
Definitely not. The questions are specifically crafted to push memory-based reasoning. They break them down into 5 key types.
All right, let's hear them. What's the first type?
Multi-detail reasoning. This needs the agent to pull together multiple pieces of information scattered across the video. An example might be looking at the 5 products reviewed, which collection had the highest starting price. You can't answer that by just looking at one spot.
Okay, needs aggregation. What's next?
Multi-hop reasoning. This requires step-by-step logical deduction across different parts of the video. Like, they visited several cafes. Which bubble tea shop did they go to after visiting the one called Ding Cha? Need tracking sequences.
Right, following a chain of events. What about using different senses?
That's cross-modal reasoning. This tests the ability to combine visual information with auditory information, like dialogue. For example, seeing different colored folders while hearing someone talk about confidential documents, and then answering, which color folder is for confidential files?
Ooh, tricky. Integrating sight and sound.
Then there's human understanding. This is really interesting. It probes reasoning about people, their identity, emotions, skills, intentions. Like, based on how Lucas was cooking, would you say he's skilled or a novice? That requires some nuanced interpretation.
Wow, that's moving towards social intelligence. And the last type.
General knowledge extraction. This tests if the agent can derive broader world knowledge from specific events it observes. For instance, after watching someone put vegetables on a specific shelf in the fridge, asking which shelf is generally suitable for storing vegetables.
So learning general rules from examples. Okay, these sound way more challenging than typical QA. How many questions are there?
There are over 1,500 QA pairs for the robot videos and over 5,000 for the web videos.
Okay.
And importantly, they're all open-ended questions. The AI has to generate the answer, not just pick A, B, C, or D.
Okay, that's a serious test. So the moment of truth. how did M3 Agent actually do on M3 Bench and other benchmarks?
The results were really quite strong. They evaluated M3 Agent on both parts of M3 Bench, robot and web, and also on another benchmark called video ME long. And the headline is, M3 Agent consistently outperformed all the baseline methods they compared it against.
All of them, including the strong ones using GPT-4o and Gemini.
Yes. Compared to the best baseline, they constructed a hybrid using both Gemini 1.5 Pro for perception and GPT-4o for reasoning via prompting M3 Agent, showed significant accuracy gains. It was 6.7% higher on M3 Bench Robot, 7.7% higher on M3 Bench Web, and 5.3% higher on video ME long.
Those are pretty solid margins. Were there specific areas where it really shone?
Definitely. Its performance was particularly impressive on the human understanding questions, remember, reasoning about people's skills or emotions. It showed a huge 15.5% gain over the baseline on M3 Bench Web for that category.
Wow, 15.5%.
And also on cross-modal reasoning, combining sight and sound, where it had a 6.7% gain on M3 Bench Web. This really backs up the idea that its architecture, especially the entity-centric memory and multimodal integration, is effective for these complex reasoning tasks.
That makes sense. It links back to its ability to maintain character consistency, understand nuances about people, and weave together visual and auditory information. But, seeing good results is one thing. Did they dig into why it works? You mentioned ablation studies earlier.
Absolutely. The ablation studies are crucial for understanding which components are really driving the performance. And they revealed some key things. First, semantic memory is vital.
The general knowledge part.
Exactly. When they removed the semantic memory generation component, accuracy plummeted by 17.1% on M3 Bench Robot, for instance. This really hammers home that just remembering specific events isn't enough. You need that layer of generalized world knowledge.
Okay, so semantic memory is critical. What else did the ablations show?
The reinforcement learning training using DEAPO really matters. Getting rid of the RL fine-tuning also caused a significant accuracy drop, about 10.0% on M3 Bench Robot. This proves that training the agent to learn how to iteratively query its memory is much better than just a fixed strategy.
So the learned reasoning policy makes a big difference.
A big difference. And finally, other specific design choices like the inner-turn instruction prompting and the reasoning mode itself were also shown to be critical. Removing them led to drops of 10.5% and 11.7% respectively on M3 Bench Robot. So basically, all the core components they designed seem to be pulling their weight.
It sounds like a well-thought-out system where the pieces really work together. To make this even more concrete, let's look at some examples. Can you walk us through a case study of the memorization part in action?
Sure. They showed how their memorization model, Memory 7 BSF, compares to a baseline. The M3 Agent model generated much more detailed episodic memories, richer descriptions of scenes, what characters were doing, their expressions, even quoting dialogue more accurately.
So better observation skills, essentially.
Better observation and better recording, yes. And importantly, it showed much better identity recognition. It was better at consistently identifying people across clips and, crucially, linking their face to their voice.
The entity linking we talked about, getting Alice right every time.
Exactly. And beyond just the episodes, it extracted richer semantic memory. It would proactively generate knowledge like Alice prefers coffee or this room is the kitchen, building that world model more effectively than the baseline.
Okay, that shows the memory building. Now, what about the control process using that memory? You mentioned an example with a character named Tomas and a question about his imagination.
Yes, that's a great example of the multi-turn reasoning. The agent gets the question, is Tomas a person with rich imagination or someone who lacks imagination? Quite abstract.
Yeah, not something you'd find directly stated usually.
Right. So first turn, the agent uses search node maybe to find Tomas's internal character ID. Let's say it's character 4.
Okay, identifies the entity.
Second turn, it might try a direct query based on the question. What is character 4's personality regarding imagination?
And let's assume the memory doesn't have a specific node labeled imagination level.
Exactly. That query probably returns nothing useful. Now, a simpler system might just give up. But M3 Agent, in the third turn, reasons. It knows from memory that Tomas, character 4, is, say, the CTO of a tech company. Based on that role, it formulates a new, smarter query.
It adapts its search strategy. What does it ask?
Instead of imagination, it asks something like, what are character 4's creative problem-solving methods? Or describe character 4's approach to innovation. This is a much more targeted query based on his likely activities as a CTO.
That's really clever. It's inferring related concepts.
Precisely. And this query might successfully retrieve relevant semantic memory nodes, perhaps stating Tamaz is known for being innovative and forward-thinking, or mentioning his work on scaling drone technology for personal flight.
Okay, now it has useful evidence.
Right. So by the fourth turn, having gathered this evidence through its iterative, reasoning-driven search, the agent has enough information in its working context to confidently answer the original question. Yes, Tamaz appears to be a person with rich imagination.
That really illustrates the power of that multi-turn adaptive reasoning. It's not just matching keywords, it's problem solving.
It's a huge difference. It allows the agent to uncover relevant information that might be indirectly related to the original query, something a single-shot Argus system would almost certainly miss.
Okay, M3 Agent is clearly very capable, but no system is perfect. What did the researchers identify as limitations or hard cases where it still struggles? What's next?
They were quite upfront about the challenges, which point towards future work. Two main areas stood out in the M3 bench evaluation. First, reasoning about fine-grained details.
Fine-grained details? Like what?
Questions like, who specifically wanted to eat the ham sausage out of a group of people? Or which specific hook on the coat rack should Emma's hat be placed on? These require remembering very specific, possibly minor details.
And that's hard because the agent can't possibly remember everything, right? It would be overwhelming.
Exactly. You need selective attention. The paper suggests future work should focus on developing better mechanisms for selective memorization, allowing the agent to prioritize potentially important details, perhaps guided by the task, and building more task-specific knowledge.
Okay, better attention and focus. What was the second challenging area?
Spatial reasoning. Questions like, where in the kitchen can the robot find the snacks? Or, is Leo's water cup on the second shelf or the third shelf right now? These prove difficult.
Why is spatial reasoning harder?
Well, think about it. Describing spatial relationships accurately using just text or even abstract representations can be really inefficient and imprecise. Visual memory is often much better for that. So the suggestion is that the long-term memory needs to incorporate richer visual content.
Like actual snapshots or maybe even 3D maps of the environment?
Potentially, yes.
Yeah.
Storing key visual snapshots or building some form of spatial map within the memory could provide the grounding needed for more robust spatial reasoning about object locations and layouts.
That makes a lot of sense. Okay, let's wrap this up. What's the big takeaway here for you, the listener, and for AI's future?
M3 Agent really feels like a significant step. It's a concrete demonstration of multimodal AI that gets much closer to human-like long-term memory, continuously learning, building both specific, episodic, and general semantic knowledge, and then effectively reasoning with that memory. An M3 bench provides a solid way to measure progress in this area.
And why does this matter practically?
Because it moves us closer to AI agents that can genuinely understand and interact with complex environments over long periods. Think about household robots that don't just follow commands, but actually learn your habits, anticipate needs, and adapt to changes in the home. Or general-purpose AI assistants that build a real understanding of your projects or interests over time. It's about moving beyond simple task execution towards genuine understanding and collaboration.
Right. So here's a final thought to leave you with, something to maybe chew on. If we keep improving these agents, giving them better selective attention, richer visual and spatial memory, they won't just remember things about our world or even about us. They'll start to truly understand and adapt. What happens when AI agents become indispensable companions, potentially knowing our patterns and preferences even better than we know ourselves? Where does that lead?
That's the million-dollar question, isn't it? Exciting and maybe a little unsettling to think about.
Definitely something to ponder. That brings us to the end of this deep dive on M3 Agent. Thanks for tuning in to AI Paper Podcasts.
Thanks, everyone.